Welcome to YQ Academy, SQL Interview Questions and Answers. 1. How many clustered indexes can be created on a table? In SQL Server, you can create only one clustered index per table. A clustered index determines the physical order of the data in a table, and as such, it defines the logical storage structure of the table. The clustered index determines how the data is physically stored on disk, with the rows of the table being organized in the order of the clustered index key. Because the clustered index affects the physical storage and order of the data, there can be only one clustered index on a table. The clustered index key is unique for each row in the table and determines the physical location of the data on disk. However, it's important to note that a table can also have one or more non-clustered indexes. Non-clustered indexes are separate structures that store a copy of selected columns and their corresponding row pointers, enabling efficient data retrieval based on those columns. Unlike the clustered index, non-clustered indexes don't determine the physical order of the data and can be created on one or more columns. 2. I create a separate index on each column of a table. What are the advantages and disadvantages of this approach? Advantages. 1. Column-specific indexing. Creating individual indexes on each column allows for efficient searching and retrieval based on specific columns. Queries that involve filtering or sorting on a particular column will benefit from having an index dedicated to that column. 2. Improved query performance. With indexes on each column, queries that involve multiple columns can potentially use multiple indexes simultaneously, leading to improved query performance. This is particularly useful for complex queries with multiple filtering conditions. 3. Flexibility. Having separate indexes on each column provides flexibility in query design. You can choose which columns to include in the queries where clause or join conditions, and the corresponding indexes can be utilized to optimize query execution. Disadvantages. 1. Increased storage space. Creating an index for each column requires additional storage space. The size of indexes can be substantial, especially for tables with a large number of columns. This can lead to increased storage requirements for the database. 2. Insert and update overhead. Whenever data is inserted, updated, or deleted in a table, the corresponding indexes must be maintained. Having multiple indexes means that these maintenance operations will take longer and may impact the overall performance of data modification operations. 3. Index maintenance overhead. Managing multiple indexes introduces additional maintenance overhead. As the table data changes, the indexes need to be updated accordingly. This can impact the overall performance of the database, especially during bulk data modifications or frequent data updates. 4. Index fragmentation. Creating separate indexes on each column can result in index fragmentation. Index fragmentation occurs when the physical order of index pages becomes disordered due to insertions, deletions, or updates. Fragmented indexes may lead to decreased query performance and increased storage requirements. 5. Index selection overhead. With a large number of indexes, the query optimizer might face difficulties in selecting the most appropriate index for a given query. The optimizer's decision-making process becomes more complex and time-consuming, potentially impacting query execution time. 3. What is RAID and what are different types of RAID configurations? RAID redundant array of independent disks is a technology that combines multiple physical disk drives into a single logical unit to enhance performance, reliability, and /or data availability. RAID configurations provide different levels of redundancy, data striping, and fault tolerance. Here are the commonly used RAID configurations. 1. RAID 0 striping. RAID 0 improves performance by striping data across multiple disks. It splits data into small blocks and distributes them evenly across the drives in the RAID array. RAID 0 does not provide any redundancy or fault tolerance. If one drive fails, the entire array can become inaccessible, potentially resulting in data loss. 2. RAID 1 mirroring. RAID 1 provides data redundancy by mirroring the data across multiple drives. Each drive in the RAID array contains an exact copy of the data. RAID 1 offers high read performance as data can be read from any drive in parallel. However, it has lower write performance due to the need to write data to multiple drives simultaneously. RAID 1 can withstand the failure of one drive without data loss. 3. RAID 5 striping with parity. RAID 5 combines striping and parity to provide a balance of performance and fault tolerance. Data and parity information are distributed across all drives in the array. Parity information allows for data reconstruction in case of a drive failure. RAID 5 requires a minimum of 3 drives and can tolerate the failure of a single drive without data loss. However, the performance may be impacted during the rebuilding of data after drive failure. 4. RAID 6 striping with dual parity. RAID 6 is similar to RAID 5 but provides higher fault tolerance by using dual parity. It requires a minimum of 4 drives and can tolerate the failure of up to 2 drives without data loss. RAID 6 offers better protection against data loss compared to RAID 5, especially in environments with larger capacity drives where the chances of a second drive failure during rebuilding are higher. 5. RAID 10 striping and mirroring. RAID 10 combines the benefits of RAID 0 and RAID 1. It stripes data across multiple mirrored sets of drives. RAID 10 provides excellent performance due to striping and high data redundancy due to mirroring. It requires a minimum of 4 drives and can tolerate the failure of one or more drives within each mirrored set without data loss. 6. RAID 50 and RAID 60. RAID 50 and RAID 60 are combinations of RAID 5 and RAID 0 striping with parity or RAID 6 and RAID 0 striping with dual parity, respectively. These configurations provide higher performance and fault tolerance compared to RAID 5 or RAID 6 alone by striping data across multiple RAID 5 or RAID 6 arrays. 4. What are the steps you take to improve performance of a poor-performing query? 1. Identify the problem. Determine the specific query that is performing poorly and identify the performance issue. Is it slow execution, excessive resource usage, or high disk/O? 2. Analyze query execution plan. Examine the query execution plan to understand how the database engine is executing the query. Look for any inefficient operations, missing or incorrect indexes, or large data sets being processed. 3. Optimize the query. Review the query itself and consider making changes to optimize its execution. Look for opportunities to simplify the query, eliminate unnecessary joins or subqueries, and reduce the data being retrieved. 4. Evaluate indexing. Analyze the query execution plan and identify any missing or underutilized indexes. Consider creating or modifying indexes to improve the query's performance. Ensure that indexes are properly designed and cover the columns used in the query's filtering, sorting, and joining operations. 5. Update statistics. Outdated or inaccurate statistics can impact the query optimizer's decisions. Update the statistics on the relevant tables and indexes to ensure accurate cardinality estimates and optimal query plans. 6. Partitioning. If the table being queried is large, consider partitioning it based on a specific column. Partitioning can improve query performance by allowing the database engine to access only the necessary partitions instead of scanning the entire table. 7. Revisit database schema. Assess the database schema and table design. Ensure that it is properly normalized and the relationships and constraints are appropriately defined. In some cases, denormalization or restructuring the schema may be necessary for performance improvements. 8. Hardware and server tuning. Evaluate the server hardware and configuration settings. Ensure that the server has sufficient memory, CPU resources, and disk/O capacity to handle the workload. Adjust server configuration parameters, such as memory allocation, parallelism settings, and query timeout thresholds, to optimize query execution. 9. Testing and benchmarking. Implement the suggested optimizations and test the query's performance. Compare the execution time and resource usage before and after the optimizations. Use benchmarking tools and techniques to measure the impact of the changes accurately. 10. Monitor and fine-tune. Continuously monitor the query's performance, gather performance metrics, and address any ongoing performance issues. Use database monitoring tools and performance counters to identify bottlenecks, resource contention, or changes in query behavior. This is the end of our SQL interview questions. We hope you enjoyed learning with YQ Academy. Until next time, goodbye.